All right, today's algebra lesson is over 6.1, which is solving systems by graphing. Now, we've never talked about systems before, but all it means is two different lines. So you can see down here a little preview, two different lines. This would be called a system of equations. So our first picture has skiers on it. It says there are two professional downhill skiers and they are racing at the speeds shown in this diagram. So this first skier looks like he's a little bit ahead, but is only skiing 100 feet per second. And this skier that's a little bit behind is skiing much faster, 110 feet per second. So, oh, this is why. It says skier 1 started 5 seconds before skier 2. So they're cheating, but that's okay. That's why this skier for now is in front. The course is 5,000 feet long. Do you think that skier 2 will pass skier 1 if they get to go 5,000 feet? I hope you decided yes, you think that it will, because if you're going 110 feet per second, you will definitely pass someone going only 100 feet per second if you're just 5 seconds behind them. When exactly will they meet? That is why we use graphs, because where they meet is their intersection point, which is the entire lesson that we're talking about today. So you can model the problem above with two linear equations. Two or more linear equations form a system of equations. That means two or more. System of equations. And then if you find that ordered pair that makes all of the equations in a system true, it is called a solution. So if we look down at the next graph, at the graph down here, this 2, 4 is where they meet, and that is true for both equations. It has a 2, 4 in this equation, and it has a 2, 4 in this equation. So because 2, 4 works for both equations, it's where they intersect. 2, 4 would be the solution. So what is the solution? 2, 4. It's where they meet. It also says you can check by plugging it in. I'm only going to show you how to do this once because it takes a little bit of time, but I think you should be able to check your work. So 2 is my x coordinate and 4 is my y coordinate. So if I were to plug in 2 for x and 4 for y, this problem would need to be true. And 2 plus 2 is 4, which is true. But it needs to be true for both equations. So let's plug in 2 for this x and 4 for this y and see if this is also true. 3 times 2 is 6. 6 minus 2 is 4. So it is true for both. So again, you can check it by taking your two equations and plugging in your two solutions to make sure it's true for both. Or if you're lucky enough to have it graphed, you can see that it's true for both because it's right there where they intersect. Okay, moving on to part 2. You have to graph it now. I'm going to actually zoom in on this so that you can see the graph a little bit better, because right now it's pretty far away. We have had a lot of practice on graphing equations, especially if they're already in slope-intercept form, which both of these are. So let's just graph them. First, you put a dot at 4 on the y-intercept. That's your b. That's your y-intercept. 1, 2, 3, 4. And then you're going to count slope. 2 is the fraction 2 over 1, rise over run, up 2 over 1, up 2 over 1, up 2 over 1. That's a little bit off the paper, and then you can still go back. So continue that pattern going down 2 over 1 in the other direction as well. The more dots you get on your paper, obviously the straighter your line's going to be without a ruler, which I'm not using one. And then let's graph our other line. First dot is at 2 on the y-axis. So, in fact, I'm going to use a different color just so I can tell my difference. 2. And then the slope is 1. It's a hidden invisible 1. If there's not a number there, it's 1. And a fraction would be 1 over 1. So from this dot, I'm going to go up 1 over 1, up 1 over 1. And I'm going to keep going all the way. And then I'm going to go back the other direction. And right where those two dots meet, I'm going to circle it and make it more of a bigger, like a bullseye. And so I can find that number a little quicker here in just a minute when I want to find what the solution is to these two equations. Okay, so there's my two lines. Let's see what bullseye that's on. That is on -2, 0. -2, 0. So when I come over here and it says we graphed both equations, we found their point of intersection, and that is the solution, which was -2, 0. All right, and again, you can check by plugging them into these equations, but if you find it on a graph, that's where it's at. Okay, part 3 is a word problem about 2 alligators. So it says scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below, here in this little diagram. After how many months did the alligators weigh the same amount? So if you're trying to find the place that they are the same, it's just like going up here and finding the place that they intersect, the place that is true for both equations. So we're trying to find, if we graph this, the place where they would meet. So alligator 1 has an initial weight of 4 pounds. That would be like my B. That would be my y-intercept. And my rate of growth is 1.5 pounds per month. So that would be my M, or my slope. So it's 1.5 pounds per month plus 4, which is where they started tracking it from. Over here, we've got another alligator. The slope would be 1 pound per month. And they started at their B, their y-intercept. They started recording alligator 2 once it was at 6 pounds. So let's first write equations for both alligators. Alligator 1 is y equals 1.5 is my slope, so 1.5x plus 4 is where it started from. Okay? Alligator number 2 is y equals 1x, because 1 is the slope. You can leave that 1 off of there if you want. Plus where it started, which is 6. Okay, and then it says go ahead and graph these 2 equations. So I'm going to start my first alligator. I should have made it the second alligator in a different color. That's okay, I'll do this super quick. All right, so my first alligator, the blue line, I'm going to start with my first dot at the y-intercept, which is 4. So 4, alligator 1 started at 4. And its growth rate is up 1.5 pounds per month. I should have labeled this as pounds per month. So this is going to be my pounds. Time is always independent, so anytime you have months or seconds or anything like that, it needs to be on the x-axis. So it is going 1.5 pounds in the next 1 month, and then 1.5 more the next month, 1.5 more, then 1.5 more, and I'm just going to keep going until I end up being a little bit off the chart. So I'm going to assume that this alligator is going to continue to grow. At some point, obviously, it will stop growing, but I'm going to put an arrow because it's probably going to keep going after several months. Okay, then I'm going to get out my purple line, and I'm going to put my first dot at 6 because they started measuring this alligator once it was at 6 pounds, and then it only grew 1 pound per month. So 1 pound in 1 more month, 1 more pound, 1 more month, 1 more pound, 1 more month, 1 more pound. Okay, I see right here I'm going to hit the same dot. So I'm going to give it a little bit of a bullseye just so that I can find it a little quicker. And then when I draw my line this direction, I can clearly see that they cross each other because one kind of, even though it started heavier, it's not growing at a rate quite as quick as my one that started with fewer pounds. Okay, turn it over to the back. Oh, I forgot to answer the question. It said, when did the alligators weigh the same amount? That would be the intersecting point. At 4 months, they both weighed 10 pounds. So at 4:10, but that doesn't really answer the question. It just shows that where they intersect. At 4 months answers the question. So after how many months did the alligators weigh the same? After 4 months. Okay. All right, turn it over to the back. Key vocabulary is, I'm going to have to widen this out a little bit. The key vocabulary is consistent, and that is when a system of equations has at least one solution, which we've been finding all of these are consistent because they have one solution. They intersect in one place. A consistent system can be either independent or dependent. A consistent system that is independent has exactly one solution. So all of the ones we did on the front of this worksheet were consistent and independent. For example, oh, I just said that. The systems we did today are both. However, a consistent system that is dependent would have infinitely many solutions. Think about that. What would a graph look like if both of these lines met every single spot? Infinitely. If instead of just meeting in this one graphed spot, if the dots met everywhere. Think about what that type of a graph would look like. And then lastly, a system of equations that has no solution is inconsistent. So again, go back to the front. What if these never met? What if there was no solution to either one of these two lines? Think in your head about what those two lines might look like. And now let's figure it out on the back. So I'm going to zoom back in. This is systems with infinitely many solutions or no solution. So here we go with this one. Let's graph it. All right, I'm definitely going to graph this bottom one first because it's already in slope-intercept form. So put a dot at my +1. And my slope is up 1 over 2. So up 1 over 2. Rise 1, run 2. 1 over 2. That was off the paper. That's okay. Go back down 1 over 2 in the other direction until you can get as many dots on there as possible so that we can have as straight of a line as possible. All right, the problem with this top one is you can't graph it unless it's in slope-intercept form. So I am going to have to rearrange it to get y by itself. So first I'm going to add x. I'm going to leave 2y alone. I'm going to add x to both sides. And I'm going to put the x first, +2. And then lastly, to get y by itself, it's being multiplied by 2. I'm going to divide by 2. Remember on this right side, when you divide by 2, you have to divide both parts by 2. So that is a hidden invisible 1 there. So 1 over 2x, I'm just going to leave it 1 over 2x. And then 2 divided by 2 is 1, +1. So now I can graph it. So this second graph has a y-intercept of 1. Oh, that's where they intersect. And it's up 1 over 2, up 1 over 2. So up 1 over 2. Oh, they intersect there too, and there, and there, and here, and here. They intersect everywhere. So this is an example of infinitely many solutions. So anytime you can think of a graph that would touch everywhere. It doesn't just touch in these dots that I made. It also touches in between. It's the entire thing because they're the exact same line. So that's why there are infinitely many solutions, because it touches infinitely in every single spot. All right, let's try the second one. These are both in slope-intercept form, thankfully. So I'm going to go ahead and start by graphing this top one. First dot at +2. And then the slope is 2 over hidden invisible 1. So up 2 over 1, up 2 over 1, down 2 over 1 the other direction to keep the pattern there. All right, and then our second equation, our first y-intercept is at -1. So that's right here on the y-axis. But my slope is still 2, so it's still 2 over 1. So it's still up 2 over 1, up 2 over 1, up 2 over 1. I'm going to keep going down 2 over 1 the other direction. So these two form interesting lines. They will never intersect because the lines are parallel. The slopes are the same, which we've talked about, same slopes before being parallel lines. So since these will never meet, if I ask you what the solution is, meaning where do they meet, and you say never, what you're telling me is there is no solution. There's never a solution that these two equations would be at the same spot at the same time. All right, let's do this last one. I'm going to graph the top one first because it's already in slope-intercept form. So I'm going to put my first dot at -3, and then the slope is up 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. Can almost get one more dot on there. And then the second equation I'm going to do off to the side because it's going to have to be rearranged. 3y equals 9x minus 9. To get y by itself, I will need to divide both sides by 3. Remember, when you divide both sides by 3, both of these terms have to be divided by 3. So 9 divided by 3 is 3x. and negative 9 divided by 3 would be minus 3. So I'm going to put my first dot at negative 3. Oh, there you go. And then this slope is up 3 over 1. 1, 2, 3 over 1. Same thing here. It's going to be the exact same line, which means where do they meet? Everywhere. They meet in infinitely many solutions places. That was a lazy way to write it, or like this. Okay, that's okay. As long as you know it's infinitely many solutions because they meet anywhere, everywhere. All right, so here's a quick recap of everything we've done today. We have learned 3 different types of graphs. We have learned a one solution, which means they intersect in exactly one spot. We've learned infinitely many solutions, which means they meet everywhere. There's 2 lines there. It's hard to see, but there are 2 lines there. And then we have a no solution, which are parallel lines, meaning they will never meet anywhere. All right, here's some you try. This is a great time to push pause on the video and try it yourself, and then fast forward and see if you did these correctly. If you're not quite ready to try it on your own, I can definitely do them with you right now. All right, a reminder of a y equals 2x. If there's nothing afterwards, that means there actually is a y-intercept. It's just that it's 0. So I'm going to put my first dot at 0 and go up 2 over 1. Up 2 over 1. Down 2 over 1. I'm just going to keep going as many dots as I can get on there. And then we've got the next equation. My first dot is at positive 4. And the slope is negative 2 over 1. So I'm going to go down 2 over 1 from this dot. Down 2 over 1. That's where they meet. Down 2 over 1. Down 2 over 1. Down 2 over 1. As many dots on there as you can, arrows at both ends of your lines. So this one has exactly one solution, and that one solution is 1 up 2. So the solution is, so first of all, there's one solution, and it is 1 comma 2. All right, let's look at the next one. I'm going to graph the top one first because it's already in slope-intercept form. I'm going to put my first dot at 1 on the y-axis, and then my slope is up 1 over 2, up 1 over 2, up 1 over 2, and then keep going down 1 over 2 the other direction as long as your pattern stays the same, straight line, arrows on both ends. And this guy I'm going to have to rearrange. So I just need to get y by itself, so all I need to do is subtract that x to the other side. And then it'll be done because y will equal negative x and positive, so plus 4. So my y-intercept is 4. And my slope is down a hidden invisible 1 over 1. So down 1 over 1, down 1 over 1. Oh, that's where they meet. Down 1 over 1. And keep going to get as many dots on the paper as you can. So once again, we have one solution. Exactly one solution. And that one solution is at 2, 2. I believe that's over 2 up 2. Sorry about the interruption right now.
This time as the 8th grade girls basketball team needs to be released for their game this afternoon.
Good luck, 8th grade girls basketball.
Best of luck. This time 8th grade girls basketball release. Thank you.
Okay, sorry about that. Okay, we need some review over an x equals and a y equals. An x equals is going to be a vertical line. A y equals is going to be a horizontal line. And I want to show you in case you forgot. If you forgot which direction which is, let's go ahead and just do a mini table real quick. This doesn't take any time at all to do a mini table. And what you do is, this means every single x needs to be negative 3. So negative 3, negative 3, negative 3. And then just pick whatever you want for y. Let's try 0, 1, 2. And then graph these dots. Negative 3, 0 is right here. Negative 3, 1 is right here. Negative 3, 2 is right here. So if you forget, go ahead and make a little mini table and remind yourself which way these lines go. So let's say I forgot that y equals 2 is horizontal. So what I would do is I would make a little quick mini table, and every single y has to equal 2. So 2, 2, 2, and then just pick whatever you want for the x's. Use some easy ones like 0, 1, and 2, and then graph these dots. 0, 2 is right here. 1, 2 is right here. 2, 2 is right here. So you can see that it's going to be a horizontal line. All right, so this again has one solution, and that means they intersected in exactly one spot. So we've got a lot of one solution practice here. And that meets at negative 3, positive 3. Negative 3, 3 is the solution. All right, last one. I'm sorry to say we have to rearrange both. So I'm going to write one kind of up here. I think I have the most room up here. So 2x minus y equals negative 1. We have to get y by itself. So let's minus 2x. Let's bring down negative y, negative 2x minus 1. Those cannot be combined. They're not like terms, so I always write the x first. And then this is a negative hidden invisible 1, so I need to divide both sides by negative 1. So that divided by negative 1 is just positive 2x. Negative 1 divided by negative 1 is positive 1. All right, so I'm going to graph this line first. I'm going to put a dot at 1, and I'm going to go up 2 over 1 for my slope, up 2 over 1. I'm going to continue to go back the other direction, down 2 over 1, just to get lots of extra dots. Okay, and then now I need to rearrange this last equation. I'll try to find room down here to do it. Negative 4x plus 2y equals 6. I need to add the 4x to the other side. I need to bring down 4x and positive 6. And lastly, I need to divide by 2 on both sides. 4x divided by 2 is 2x. 6 divided by 2, I'm out of room, is positive 3, so plus 3. But now I can graph it. Put your first dot at 3. 1, 2, 3. And the slope is up 2 over 1. Up 2 over 1. We ran out of room, so we're going to go down 2 over 1 the other direction. Down 2 over 1. And I hope that what you see is even though these are super close together, the slopes are both up 2 over 1, which means they are both parallel. And since that means they will never intersect, that means there will never be a solution to this system because they will never meet.